With
So I
AI?
have a paid, OneSparse has a paid Zoom account, so I think this will all
Okay.
just work out good. It's going to go into the
So
cloud. Let's hope. Uh,
I got a few out my window.
looks
Clouds.
good. Yeah.
Yeah,
Um,
let's go. Okay, so um, I think so. I've been doing a lot of work the past few days and this is both for you, for Vidith, to some extent for Joe, um, and Ray Kimmerer, um, on not so much rewriting or refactoring much of SuiteSparse GraphBLAS, and it's just to call it GraphBLAS because of course SuiteSparse. When I say the word
yeah,
SuiteSparse, I mean of course all my solvers. I'm not working on well, I am working on some of those, but in GraphBLAS, so when I say GraphBLAS, you know what you mean. I mean of course my GraphBLAS, right? I don't have to,
totally.
but unless I call it the GraphBLAS API, all
Or
right.
the spec,
Well, so
right?
oh, the spec, yeah. So what I've done is actually, you can see it here on this git push, I'm moving files around because I
Mm,
used to have, if I go to say, just to make it easier for us to navigate the code. So this was my source folder a week ago. All my source files for every method just packed together in one big source file. And I can navigate this because I have a naming convention, like all the select methods are GB select. Okay. AXB means matrix multiply, but they're all sort of jumbled together. Well, that's just too hard to navigate. Even it's getting hard for me. Okay. So what I have now is to make our life easier and your life easier is this is now my source folder. Okay. And
excellent.
it's way simpler to understand. And I'm still in progress of this. So I had this notion of templates in C, right? It's just pound to find a macro of some kind or a bunch of them, and then pound include a file. Okay, that works fine. It's a little aesthetically unpleasing, but there's another problem with it that I know you can get around. It's not a problem because I know what I'm including. But when you do a pound include, are you meaning to include a header file or an actual source code that you're templatizing? It's not clear necessarily
Mm,
which you're doing. I have a so my strategy for that is twofold. It used to be just, oh, it's a source code file, it's a .c, but I don't compile those .c's independently because they're not compilable independently. They have to be included in another .c. So it's a
yeah.
.c file, but it's a template source code. And .h is the header file. Okay, but I've taken that one step further and and made it more clear in when I do the pound include, it's let me go for say reduce. Here's the reduce folder. So this is the entire thing. This is not a good example, but there's no there's no includes in this maybe. But if I look for the use of the word include, okay, you'll see it looks often will look now something like this. Okay. This then is a template because it's got it in the name. It's a reduced template. It's not a include file as a header file. So those are the distinctions. You'll be able to look at the include statement to know what it is I'm doing. And I haven't finished this. So these are include files. They're not template files. And the same thing with the rest of these. And so I'm basically adding the path since I now have it subfolder, sub structured. Basically, what happens here is all of these modules, if you will, of the code, and I say that in a loose sort of sense. All of them have not all of them, but many of them have include subfolders for include files for that component. So assign include are include file header files for GRB assign, um, for EY's add, for the JIT kernels, for the math, for the memory managers, and so forth. Okay. I also have, probably more so, template files. These are template files in each of those domains. And you notice there's not actually a lot of these. There's a way more. These are where you'll find the JIT kernels, or the source code for the JITs that the JITs use. And then I also have a notion called the factory. The factory is not the JIT. The factory is things that come from the factory. That's me. I bake them in and they're fixed. They're not going anywhere. You can choose to modify the code to have not have some of these factory installed kernels. So the library is smaller. That's the compact mode, or there's a per summering and per operator and per data type control of that if you like, which FalconDB uses to reduce the size of the binary of GraphBLAS. But those are baked in, and that was where I got my performance before, was the factory. Those are my fast kernels. Now, of course, I have the factory as well. The factory I have the JIT on both on the CPU and CUDA as well. And it's this cool thing now, it's the same JIT. So I have 4 kinds of kernels then in GraphBLAS. There is, well, I guess maybe there's 5 kinds of kernels. We'll sometimes have kernels where they're factory, but they're not, you can't turn them off. They're things like ISO valued, like the ISO any pair summering or min1 summering. It's the same thing. You're just computing structural information. I have 1 copy of that version of that code, and I don't templatize it or anything. It's just baked in. And then I'll have the second kind is the factory kernels. These are large switch cases. I call them switch factories, which choose between, oh, it's this summering, it's that data type, it's this operator, and so forth. And I've got 1,000 of those factory kernels. That's why, and those are the reason why GraphBLAS takes so long to compile. That's like 3/4 of millions of lines of code just for the factory kernels. That doesn't even include the template files they bring in, because they use the template files as well, just at compile time, not runtime. The second thing after the factory kernels I have are the CPU and CUDA JITs, both. And so I'll walk you through what those, how I talk to those, how I construct those. And then the very last fallback, the slowest thing of slow, of course, you know, is and from, you know this by looking at the burble, if you ever see the word generic, you should be afraid. It's the generic kernel. And this is the method that does nothing except through, everything it does is through mem copies and calling through function pointers. Every multiply, every add, every typecast, even typecast double to int, it's through a function call, pointer even, or I have a thing called a cast factory, where I asked the factory, hey, cast factory, I have 13 squared typecasting functions minus 13, because there's 13 data types, I guess. I think it's on the order of 13 built-in data types that can cast between them. So that's 13 squared minus 13. Don't need the diagonal, or it's just a copy. So I actually have that as well. So I have 13 squared functions. I ask the cast factory, give me the function that casts from int 16 to float. Okay, I have a function pointer, and then I use that for every scalar I have to typecast. Every move of the data is a mem copy. So the generics are very slow, but they're the fallback if you have nothing. It works. You can compile GraphBLAS. You can compile it in compact mode, which means don't use any factory kernels, except the ones I can't disable. And I don't disable those. But don't enable the JIT on CUDA or GPU. And just, you get a very small binary, and it's just all generic. It will work. It'll be very tiny library. So to manage all of this, I have most of these folders will have one of 3 subfolders, and they'll all be named the same: factory, include, and template. Always. They're always named that. I'd have no other subfolders to these as well. And there's also a top level include file for include files that don't really fit any one of these. They're like GraphBLAS wide. Maybe I should be more creative and come up with a name for that and put it in a subfolder. Okay. Then the other thing is, well, how do I distinguish between what's a template file that I'm going to compile with at JIT time or pull into a factory kernel, because it's the same code, but it's not standalone, and where are the files that are actually compiled top level? Like if I want to compile GraphBLAS, well, it's It's these. That's it. That's all all the source code for GraphBLAS. Like if you compile all of that, you get libgraphblas.so. Well, except for one thing, you also have to get the factory kernels, which are outside the source folder now. They used to be inside the factory kernels as well. There, that's the entire libgraphblas.so.
Okay.
Full stop. Very simple. So it's a very consistent data structure. And then if you want to say, well, let's look at what about the template files that some of those factory kernels or JIT templates both use these same on the CPU, use these files. Sure, these are all my templates, but they're all in a template folder. Okay, so that's kind of the big picture of this. And so what do we have here? These are GraphBLAS now has been divided into these modules. Each module will have various parts to it. It'll go all the way down from the user GRB or GXB, all the way down to the very bottommost template file. So for example, probably the simplest one to look at is reduce. That's one of the simplest. Reduce to vector and to reduce to scalar is it's sitting here. With a caveat though, these modules of course rely on each other. Reduce to vector is just a matrix vector multiply, right? I mean, it's super simple that way. And so that's here in reduce to vector, but it's going to call a matrix vector multiply in the MXM, which is a lot bigger. So here's MXM. This is the top level. This is looking at all these different. MXM is a beast, matrix, and matrix vector. But you see the GRB methods are there as well. So this is GRB, MXM, MXV, and VXM, and everything they depend on, including the include files and all their template files. And their template files are a beast. There's a ton. I mean, there's how much? There's all of this. These different matrix multiply kernels that I have. So the matrix multiply is 16,000, almost 16,000 lines of code, and that doesn't include the CUDA kernels for the same thing. That's the CPU JIT kernels and the CPU factories and all the different algorithms I have to do that. So I thought it'd be useful to now, okay, some of these, and I've got a top level README in this folder as well that now I just wrote this yesterday that describes each of these modules, and it's alphabetized. It's not organized by type of module. So some of these modules are different. Like the apply folder is everything having to do with GRB apply. The different variants, apply a unary operator, apply an index unary operator, bind first, bind second, and so forth. Apply will also call transpose, because you can do like think of a Hermitian, compute the Hermitian matrix. It's complex conjugate transpose. That's a transpose and apply at the same time. I have a kernel for that because it's apply, conjugate is the operator, and transpose is the descriptor. There, you got complex Hermitian. So I actually have to talk to the transpose module and ask it to do the transpose. But oh, by the way, as you're doing the transpose, could you please apply an operator? Sure, transpose says, because it's a mix of the two, if you will. But that algorithm is in the transpose module. I have a method called transpose with an operator. So this is doing the work of a GRB apply and transposing at the same time. It's one call to GRB apply, but it's talking to the transpose module to do that. So what I don't have here is a nice distinction between a method like apply and assign and helper modules, which like aliased. Okay, this maybe could go in the matrix module, because this is a module that has everything to do with asking the question of I've got a matrix. Are there any components in it that are what I call shallow? A shallow matrix is not something that goes to, and I know I'm kind of bouncing all over. I'm trying to focus my thoughts here, maybe too deep, but it's a shallow matrix is a matrix which has components in it that it doesn't own. Somebody else owns it. Another matrix owns it. And this is useful only internally, but it's very useful because I might make a shallow copy of a matrix that I say I need to do a typecasting on. And then when I'm done, I'll throw it away. But I don't have to copy the integers. I can just have to make a new array for the entries, the data values. And that saves me a lot of time just by saying, well, this integer array that this matrix has over here, it's not yours. It's somebody else's. And I have a flag inside the matrix that tags that pointer as non-owning. I don't own that in this one matrix. So this is just as an example, the alias folder is a very tiny thing. It's everything having to do with asking these questions. It's very small. And it's sort of a helper module, whereas these two things, apply and assign, these are primary modules that are supporting a end user operation, GRB apply, GRB assign. And then this one is different. This is everything having to do with the binary operator, like binary op new, binary op free, binary op queries. So binary op things like, hey, this is some of my previous methods, GXB, get set sort of things. Get set, though, is another module by itself. All the get sets. So the operation on a binary operator, you can do get on that binary operator. Well, that's going to be in here in the get set module. I kind of put them all. So it's organized a little bit by theme. So this is a method, GRB binary op get. Do I put it in a binary op module or the get set module? The code's there. It doesn't change where it is. It's just organizational. And I decided to put all the get sets together.
Yeah, and don't worry
And
about bouncing around because we'll be able to. This is gonna be on multiple sessions, and we can cut and paste. And
yeah.
yeah.
So, but I wanted to sort of give you a big picture of the code structure first, and then dive in. And I thought when I was thinking about talking to you about GraphBLAS, and also had the same issue with Vidith, same issue with talking with Joe, same issue with, when I work with Ray on the code. People are starting to touch the GraphBLAS code and commit to it. It needs to be organized better so it's a little more coherent, that you can focus your mind on one piece of it, and then those pieces are what you see here. Those are all the
I think it's
pieces.
great because it's been a challenge for me as well. Like I'm
Yeah,
and I'm using Emacs's grep find all the time to sort of like, oh, where is
right.
this? Where is this? Where is that? And I'm
Yeah,
constantly grepping and not really having a mental map.
exactly. Well, now with the mental map will be easier. So if I look for, include, now I haven't finished yet. Okay, you can see all my referring to templates will now eventually, not they don't yet, right? These don't yet have the full path. Okay, but these
Mhm.
these do. I'm working towards that. So you can say, well, oh, reduce to scalar. Where do you live? Why are you including this file, Tim? Oh, it's a template. I actually have it in the name here, but I'm not consistent with that word template in the name of the file. But now I'm consistent with this folder position. All the template files are in a subfolder called template. So you can look at this and say, it's a template. Or you can look at this and say, it's a header file. And not only is it a header file, it's part of the monoid module, if you will. And that's where you'll find it in source monoid. Um, so that's helping to deal with the complexity of the code base. You can then focus more carefully on just the thing you're looking at. Now, reduce to vector suddenly says, "Oh, I want to bring in the matrix multiply, please." What? Oh, yeah, because it's a MXV. It's totally different than the others, but it's in the reduced because it is reduced to vector. I just segue over and say, I'm not going to do it. I'm going to call the matrix multiply to do it. So that will get only better with time because this should say binop binary op / include, because that thing is in the binary op include folder. Oh, no, it's just in binary op. It's okay. So wait, no, it's not here. Where is it? Binop. Oh yeah, there it is. It's here, and there's two places where these include files live actually. So there's include files at the module level, like binop.h. Like, why shouldn't that be in a subfolder called include? Well, there's a reason for that. These are the primary include files are needed at compile time only. They're not part of the JIT. And so when I say I want to build my JIT package, source code for everything the JIT kernels need, those things will always go in. MXM is another good example. So I have some header files called mxm star.h. These are files that don't go to the JIT. But if you look at mxm include, there's a ton of include files that the JIT needs to compile its kernels. That's the distinction between header files, where they go. And I don't know, but I mean, I could reorganize this further, but that's the difference right now, is if you see files at the top level of a module, those are include files because they're .h that don't go, that the JIT doesn't need. And then things inside a subfolder called include, these all go, and there's no C files in here, they're just H files. These all go to, in fact, there's a one page of them here. These all go to the JIT. The JIT needs these. The
And
JIT
you
kernels all need those.
compress those all into like a
The JIT, yeah,
header ball, right?
the JIT package, correct.
Yeah.
I could show you how that works. And I dump all this in your source folder. I'm sorry, I dump this all in your cache folder, but now it's looking more clean. I have a source folder, and now look what it is. It's almost empty. It's not empty. It's got all my code in it, but it's now all organized into two main subfolders, include and template. Because in the JIT, everything is a template.
Mm-hmm.
Even the top level. Now this is not organized. I dump it all in one place. I don't subfolder this thing because I just stick it all in. No one needs to look at this. So I just dump it all in a mishmash. So I put them all together, apply, matrix multiply, everything. They're just all stuffed in here. And the top level JIT kernels are here too, because they're templates as well. But the CUDA is not put there yet because I haven't reorganized the CUDA folders. Eventually, this might just be three, the GraphBLAS header file, the include file, and the template file, and that's it. So it'll just be subdivided into those two things. And the only difference between the include and the template is include, there's no C files, and the template, there's no H files. That's all.
Mm-hmm.
And the CUDA is a little bit different. If I do, there's no, let's see, the H files. Yeah, there's some CU. I've got to get a better naming system. QH is a CUDA header file, I guess, right? Okay.
Right.
But in the template, if you look at, but we also tend to use HPP as well. It's like, but that's also running through NVCC. So this probably should be .cuh, not HPP. So I haven't fully fixed all the CUDA because it's not in production yet. But that's kind of a little weird. And then in the template, there's some CUs there too. That's probably misnamed. If I follow my naming convention, those should be .cu, not CUH. They are templates, okay, and they're pound included, just like all my other templates. So they shouldn't be called QH because in templates are also, we also have these files. These are also templates because you pound include them to compile them in the JIT kernels for CUDA, but they're .cu. So what's the difference, right? I just need to have a more consistent naming scheme between the CUDA files, and that's in progress. So we're not gonna. I don't want to dive into the CUDA stuff. That's the reorganization the organization that's going to change. Now that I've kind of settled on an organization with the CPU source files, I'm going to then take that to the CUDA files eventually as well. I've started to do that, but I haven't finished that.
when I was thinking we could have a JIT session and a CUDA session,
Yeah,
um,
exactly.
and
Exactly.
potentially a like data structure session. Um,
Yeah, right.
there is just as a side note on that, several of the sort of accelerator sparse uh, multiplication accelerator papers that have been written,
Mm-hmm. Mm-hmm.
which I know I said I'd send you some links, and I'll do that. Um, don't use essentially a modification on CSR that allows better streaming. Um,
Oh,
one is
oh, they
called
kept,
Scissor,
okay.
and another one is like a block CSR that this other team came up with from Cornell. To just because like the FPGA accelerators often have banked memory, and to get parallel streaming out of different banks,
Mm-hmm.
CSR doesn't support that very well.
I
Um,
see.
I won't go into the details here, but
Okay.
so I can foresee for our purposes and potentially other purposes, like GPUs have essentially like shared memory is essentially banked memory because
Right.
each streaming
Right.
processor has a different bank. It
Mm-hmm.
might be advantageous to support different data structure backends. So maybe we could have a session based on that as well,
Yeah. Yeah. Um,
but not to distract
so
from this. But yeah, but if you have a
yeah,
thought on
well,
that, yeah.
I do have some thought. Yeah, I do have some thoughts on that. And I could, yes, I do, looking at the data structure for the GRB matrix in particular, like what is that and where is it? And um, and what operations, what are the core data structures and how do I convert between them and what do I support and what pending operations do I support? The idea of zombies and jumbledness and pending updates and so forth, all of that, sparse, hypersparse, bitmap, and full, and how do I convert between them and how do I access them in a generic way? Yeah, that's a huge part of
Mhm.
GraphBLAS. It's how do I template? How do I compile a JIT for those data formats? How do I support in a JIT accessing the components of a matrix?
Yeah.
I
It's like
I
every dimension
compile,
we add to the problem like multiplies
yeah,
the space of work that needs to be done.
every like when I JIT a kernel, I know at compile time the data formats of the possibly four matrices. Like one's sparse, one's bitmap, one's full, and one's hypersparse, whatever, in any combination. Each of those, it's like that's alone takes to encode that into a binary encoding. When I count my possible space of kernels, that's 4 bits each because there's 13 formats. That's, not 16, but 13. So it takes 4 bits each to encode those. So that's already, 16 bits just to encode all possible combinations of formats. That's 2 to the 16. That's 64,000 plus, right? Different variants that could be compiled.
Mhm.
And
Yeah,
I
that's
can
crazy.
compile any one of those 64,000 as well as all the other bits. Right now, it takes me 60 bits or 63 bits. I forget how many I'm using exactly to encode matrix matrix multiply. I have 2 to the 63, I think. So I'm almost running out of bits. I mean, my encoding is a 64-bit number right now,
Mhm.
and I'm gonna may have to go to 2 of them. Certainly if I do fusion, I'm gonna have to have more bits
Yeah.
uh, for the JIT. So I thought with so there's so I'm thinking about how to do the deeper dive through the code base to show you kind of the whole flow from a user call to GraphBLAS, GRB, whatever, all the way down to its execution, either with the factory kernel, the CPU, the factory on the CPU, or the CPU JIT or the CUDA JIT. I think I said CUDA already, or the generic, um, and go all the way through that. Um, I could do that. I could also, part of that is going to touch on the data structure of the matrix. And so I could do that first to show, well, here's the GRB matrix. Or I could just do the code dive and then, oh yeah, let's don't worry about the data structures. We'll get that to that later. Which order would you like to do that in?
Yeah, that's a good question. So I think from the perspective of other people eventually seeing this with their goal being to understand SuiteSparse, from their point of view, I would imagine that they're, they're coming from like, let's say a high level language like Julia or Python,
Mhm.
and they're saying A times B, and they want to
Right.
know, how do I get from A times B to whatever's going on inside SuiteSparse?
So it's a
Um,
code first, and then we'll look at the data structures as needed.
yeah, kind of top down.
Sure. Okay.
And now I know A times B is saying a lot. Like you just said, there's 64,000 combinations.
Well,
Yeah.
and it's 15,000. Like if I look at the line count for MXM, it's 16,000 lines of code.
Yeah.
And assign, how hard can assign be, right? It's just assigning one matrix to the other. How hard is that? Oh, that's 13,000 lines of code.
Yeah. So I guess, like but the simplest A times B is really, um, well, from the user's point of view, I'm not saying it's simple inside, is just, like, plus times, um, and then
But that's no difference though between plus times and any other summary ring,
and any other summary
right?
ring. Yeah.
No, there's no difference. You look at the code and it's like it's just that's the thing that happens at the very last minute. But oh
Hmm.
yeah, by the way, it's this monoid and this multiplicative operator. It's like that's like the very last stretch.
Yeah.
Everything down to that bottom is identical for all summary rings.
Yeah.
And then oh by the way, what summary ring and what data type? Is this float? Is this double? Is it int 16? Is it user defined? Oh, that's just a detail at the very end.
Well, then maybe we don't have to go all the way to the bottom. Like, another possible approach is to take like a shallow but broad approach. Be like, here's the entry point for MXM,
Mhm.
and we'll only go so deep, and then we'll look at reduce and then apply. But not go all the way to the bottom. But
Okay.
just show people the code layout. Another
Okay.
another option. So other people
Well,
that maybe go ahead.
if I did that, it'd probably be better to stick with a simpler method like reduce,
Yeah,
because that's only 1,000 lines of code.
1,000 lines of code. Okay, yeah. Um, and then maybe an idea for an alternate session, or we could start with this idea, is people who are coming to SuiteSparse with the intent to make changes and build it.
Right.
So I know there's probably an entire session we could do on CMake or more. And unless
Right.
all that is so pre-canned that there's very little thought that contributors would have
Well,
to put into it.
it's pre-canned, except there's a few twists to it. One is the JIT package, which usually gets compiled successfully. There's some cases where if you change the JIT package code itself, it may not see the changes. You have to actually delete the JIT package and recompile, rebuild it. It's not perfect on that level as when you change the code. Sometimes it doesn't reconstruct the JIT package. And the other thing that's unusual about GraphBLAS is this code generation notion I have for the factory kernels. So I have a folder called CodeGen, and you see a lot of M files there. I do my code generation in MATLAB
Hmm.
at development time, and then I push the results to GitHub in
Right.
the factory kernel. So that thing and the results of that are in the factory kernels, which is absurd amount of lines of code that's code generated. That's three-quarters of a
Wow.
million lines. Yeah. And that's not including like 1,000 of those kernels. There's 20,000, 2,000 files. 1,000 of those on order are MXM variants of different submarines. Each of those will pull in 5,000, 6,000 lines of templated code for MXM,
Hmm.
right? So that's why it takes so long to compile GraphBLAS. I'm compiling 1,000 of these are each using 6,000 lines of code from the MXM templates.
It's just, millions
But
of lines of code, like
yeah,
on the order
exactly.
of 10 million lines of code. Yeah.
Well that you're compiling, yes, and that's why it takes so long. But the code here is then. But see, I don't count this when I say how big is GraphPlus. I don't count this three-quarter million. Okay, I count this. That's important. I don't count this because that's all generated. If I look at the where I'm in CodeGen right now, no. If I say, well, how much is that three-quarter million lines of code really? Well, it's actually only 4,600 lines of code because it's all those three-quarter million lines are generated at development time from this code base.
And that's sort
This
of that
code,
combinatorial explosion of formats and types and
well, not formats, just
oh,
and types, operators, monoids, summarings, and so forth, not data formats. The data formats are handled at runtime in these factor kernels.
okay, I got you.
They're already so for example, in MXM, if I look at the MXM templates, if I look for the word sparse, you'll see this is a template method. This is an algorithm that's doing matrix matrix multiply. I call it my sax bit method. But this is a particular method that is doing Saxby level, but it's specialized. The Saxbit methods are, the output is a bitmap matrix, but it's doing Saxby operations where maybe both matrices are bitmap or one's sparse and one's bitmap. That's it. So it's that template code is only going to be used when you're multiplying a sparse matrix times a bitmap matrix or bitmap times bitmap, which is like it's like LA graph. It's like BLAS, LA pack. It's like the BLAS, the dense BLAS. It's multiplying two dense matrices together, but they're bitmapped. So
Okay.
they're sparse, but they're stored as two dense matrices. So there
In
are
the
some
bitmap case.
Yeah, right.
Yeah.
But see, that algorithm is only handling that particular case. That's kind of, but other algorithms will handle other cases of the format. So sometimes the algorithms I have will be targeted particular formats. That's why it's going to be hard to kind of separate the code versus the data, because I do very often will bifurcate into, okay, here's a bunch of kernels that only handle these particular formats. And I try to minimize that bifurcation and have algorithms that can work on multiple formats. And that's often the case where the distinction is only done at the very bottom level. And that can often be done often the case with my data structures. And that's one of the advantages of the 4 data structures I've picked. They sort of can be touched on very late. I can write it. In fact, I can write a loop that iterates across all 4 of those matrices and reading them. And building them is another, as output is another story. But reading them, you can do with one code, all 4 formats. I can walk through a matrix with a single code that I can show you that if you like, how that can be done. It's sometimes not the most efficient way of doing it, but it's doable. And sometimes I'll then be able to fuse together algorithms. Like I have one algorithm that might handle an input matrix is either sparse or hypersparse. Well, it's the same algorithm, actually. It makes a very last minute choice at the bottom level between sparse or hypersparse. And it can handle both formats.
It like
on input.
dereferences one additional hop for hypersparse,
Exactly.
right?
Exactly.
Yeah, gotcha.
And that decision for the factory kernels or for the generic will be done at runtime because there's one algorithm doing both. For the JIT kernels, it's baked in at compile time because I know the format. An if becomes a pound if you will.
Right.
So it's known at compile time. And I have a okay, so it's a lot of it's a lot of code, but I don't think of this as my own code. Right? It is my own code, but I don't. This is actually just wait, what is it? 4600. So it's much simpler than what it looks like. So what I propose to do then is to walk you through the simplest module that I can think of. Well, that's interesting. There are simpler modules like GRB matrix clear. I mean, that's so trivial. It's not even delete all the entries of a matrix. Like, okay.
Sure. Yeah, I think
I have a folder called
clear.
clear. It's 91 lines of code, right?
Right. Yeah.
I actually put it in a separate thing by itself. Whatever. Okay. It's literally line 91 codes of C. Is to pick one that's sort of in the middle called the reduce. That's what I'd like to walk you through.
Let's do it.
And what we could do is, if you think I'm getting too deep in the details, pull me back because I love the code details, right? I'll go way too deep. So how big is reduce? Well, reduce you'll find reduce here, okay, but you'll also find reduce methods in here. Here as well. Okay. And in parts of the JIT. Okay, so when we get to the code base that talks about the JIT, you'll see reduce files that support GRB reduce, but that are part of the JITifier or the part of the JIT kernels or the JIT wrappers, and those mean different things. And I'm debating about the code structure as to where these things should go. These could go all in the reuse folder, but then the JIT components are spread out, and it's kind of hard to find them. So you'll see as I walk through these three folders. There's three folders called JIT. There's the JITifier itself. Okay, this is calling out to the compiler to compile a JIT, hashing the JIT in my hash table so I can look it up again quickly. There's the JIT kernels themselves, which are the source code for the kernels. I don't compile these at compile time. There's no, everything is hidden below include and template. So these only go in the JIT package. And then there's the wrappers. These are the things that my codes call to talk to the JIT, to compile a JIT kernel, to specialize the JIT kernel and go compile it and run it. And so we'll see in here a reduced JIT, but there's other JITs. There's one per JIT kernel that I have, and there's 41 or 42, 44 on that order number of JIT kernels that I have right now. And the JIT wrappers all end with a naming convention _JIT, all of them. And so if I put these into, like, where's the reduced JIT? I could put this in this folder instead, and it would work just the same, but then it would be everything to do with reduce would be in one place. So I might do that. I might make that reorganization. I haven't decided yet on where best to organize these files. And then in the JIT kernels, there's this file as well. Okay, so let's do reduce. So you'll see reduce code both here and in the JIT folders as well. And then there's also the CUDA JIT, right? That's something altogether. That's in a whole separate file called CUDA that lives at the top level. You see the source file. These are all the CPU stuff, but it does talk to CUDA, and in particular, they're through the CUDA JIT, and in particular through these JIT wrappers, and also have a folder called gateway. This is the gateway into my backends. CUDA is just the one of them now. There's only one backend that's not on the CPU. Is the gateway. That's one file that talks to CUDA, and CUDA is its own folder. So all the CU files, they're all here. They're not in the source folder. They're in the CUDA folder, and these are not yet, of course, in production. They're still in progress, and they have their own JIT kernels, their own templates, and their own CUDA, but they're all mashed together into one thing. I don't have it broken down into here's the applies, here's the matrix multiplies, here's the EYs methods, here's the reduced methods, and so forth. I don't have those yet. Distinct made into subfolders like I do here. So let's look at reduce. That's kind of the big picture. So what happens with reduce? Suppose you call GRB matrix reduce. Now, in the very top level, I have an include file. There, that's it. This is the master include file, graphblas.h, that the end user sees. Don't edit that file because it's configured. I have a config that CMake configures. So don't ever try to edit include graphblas.h because I'll just reconstruct it from its true source. And you can see here the differences are pretty minor. It's just a few things that are important that I modify. I tag it with the version number. I I can tell the user, the end user, that I has CUDA. I have, do I have the complex C99 data type for ANSI C99 or not? Microsoft is stupid. You know, it says, do I have the Microsoft Visual C complex nastiness? And then the date, the version number, the spec, and that sort of thing. So other than that, the two files are identical. So I'll look at the include file because it's easiest. So GRB matrix reduce, and so what is GRB reduce? Well, of course, at the top level, at the very simplest level, it's just called GRB reduce, but that's of course a macro. This is GRB reduce, right? It's a generic method. And there's the use of the word generic that's not used. There's two notions of generic, right? There's this generic, which is a C notion of a generic method.
Mm-hmm.
That's a switch. It's like it's like templates on C. It's like what polymorphism for C.
Yeah,
And it's super ugly, honestly.
it is. I have to admit, it is terrible.
It is the ugliest, one of the ugliest designs I've ever seen for a language. It's like, really? You did that? Oh my gosh.
Yeah.
It's a hack. It's a complete hack into this design of C. But this is how it has to be done. And oh my gosh, this is super crazy here. But this don't try to read this. This is insanity. And it's made worse on the API. Sometimes they'll put things in the API draft, and I'll say I can't create that because the C generic polymorphism is not as flexible as C++. If you just think, oh, it's just like C, no, it's not. It's not like C++. All of these, GRB reduce is a macro that wraps all of these methods. Are you reducing a matrix to a vector via a monoid, via a binary op? Are you reducing it to a C scalar? Are you reducing it to using a monoid? Are you reducing it to a GraphBLAS scalar with a monoid? Are you reducing it to a binary, a GraphBLAS scalar using a binary operator instead of a monoid?
Mm-hmm.
Okay, all of these are folded here. And to make it worse, this scalar, each of those are 13 variants. Okay, and I have to test for all of those.
Yeah, and this is like expansion macros that expand out to
Yeah,
a
macro
bunch
to
of, yeah.
macro. Oh, it's a 3 level down deep of argument checking. You can check the type of the fourth. Like the first decision is looking at the fourth argument, which is ridiculous. Like, is it a monoid or an operator, or a
Mm-hmm.
matrix, or a vector, or a matrix? That's this first check. I have to check the fourth operator to start making this distinction. I have to make these switch cases to decide which one you're talking to. It's just absurd. And the switch cases are this. This is a switch case that's done at like C preprocessor time,
Mm-hmm.
compile time.
It's
It's
like
a
a
compile
type
time
switch, yeah.
switch. It's a type switch on, oh, and then this is and anyway, so it's a nightmare. Um, but let's suppose you call, GRB matrix reduce. You're summing up terms. Yeah, you want to get the double sum. Okay. So you call GRB matrix reduce. This is the name of a file that doesn't have the suffix because it has to do them all. So I already have to do C templates of my own inside, which are 13 of them, because there's 13 different C scalars I have to handle. So this is a highly templatized, so I just did it with a macro because I have to have the name that's different. So this is a macro that's going to do string concatenation of the prefix. So GRB matrix reduce T is bool. So this line of code. Well, actually, let's look at this one. GRB matrix reduce FP64, and I'm getting into too much details, is right here. GRB matrix reduce to the type T FP64. Oh, but I also need to have the C data type, which is double, which is right here, and it's different, right? This is FP64, and that's double. So this is constructing this method right here. It's not very obvious, unfortunately, because we're already having template nightmares. But all of them, all 13 of these, simply say, fine, I just void star. I'm going to call GB reduced to scalar. Now we get into my internal code. GB reduced to scalar. And I'm going to pass in the GraphBLAS data type of that scalar. This is a GRB type parameter. It's a GRB type object that I pass to this method to tell it which of the 13 it's doing. And so that's the very top level. And now I go to GB reduced to scalar. And I haven't yet decided. So now what I've done is the scalar is just a void star, but I know now that I have the GRB type of it. Okay. Now, oh, and I've also done some other thing. I should mention this. You'll see this word Werk lying around. It's the German, and I spelled it wrong because on purpose, because I can grep for it more easily. It's the Werk space, and that is constructed at the entry into every GraphBLAS GRB or GXB method. It's constructed actually right here in this macro, which creates this workspace. It's a statically allocated thing on the stack of like 32K bytes on that order. It's very small. And it's not added recursively. It's just there's one copy of it. It just goes stuck on the stack. And I use this for very small allocations of memory that I can then, with a push pop mechanism, I basically allocate with on a stack, my own. I have my own stack where I say, I need a scalar. Okay, stick it. I need an array of number equal to the number of threads in my OpenMP. Like I've got 40 threads. There's your tiny array of size 40. I'll put it on this Werk stack. So you'll see Werk in various places, and it's constructed here. It's not malloc, right? Statically on the stack, and then I manage that little bitty space myself, and that speeds up tiny mallocs. Although the alternative is do lots of tiny mallocs. I don't want to do that.
Is it
So,
related to the factory stuff?
No, it's totally independent. It's both. It's the Werk space is used in factory, JIT. CUDA can't use it.
Oh, because Werk in German means factory or plant.
I know it does.
Yeah. Okay.
Yeah,
Okay. All right.
I
Because
know
I
it
thought
does.
that was what confused me. Yeah. Okay. Yeah.
Yes, yes, yes. You would think, but
Right.
it's a play on
It's a play on
workspace,
words. I got you. Yeah.
and not a play on words. It's a play on well, it is in a sense work. 'Cause work in English is the word Werk in German, but it's workspace. Werk. I could have called it Werkspace,
Yeah.
Werkplatz maybe or
Right.
whatever.
I was thinking Arbeit is
Werk,
the
uh, Arbeit and Werk are there. Yeah, yeah.
like job versus
However,
work. Yeah. Right. Yeah.
yeah,
Yeah.
right. So, but I'm using so you'll see this parameter in many of my internal methods.
Okay.
So now I have to do several things. The GraphBLAS requires all kinds of error checking for, oh, you passed in a null pointer. Oh, you passed in an invalid object. Oh, you passed in a bad operator. Okay, I'll do those checks. Those checks are in the production code. Anytime you see the word assert, that's for debugging only, and it's not enabled by default. And to enable it, you actually have to edit the code. You cannot just flip a switch in CMake and turn on assertions because it would be a million times slower, literally, possibly. I don't want end users, even end developers having easy access to assertions. So there's and I could talk to you about how I turn those assertions on. I just add to one thing to this flag I would turn on, like define GB debug, and I would turn on assertions for this file only, or I could turn it on globally as well. So I have to check for typecasting compatibility. Can I typecast like you are taking an integer matrix and you're summing up with a double semi-ring, double monoid. Sure, this will say, yeah, you can do that. If you try to user-defined data type to use FP64 plus on it, I'll say, no, you can't do that, and I'll return a domain mismatch. That's not feasible.
Mhm.
Um, okay, so after the error check, then I come in and say, well, oh, and maybe I'm going too much details.
No,
I
we
have,
can go through this. Yeah.
okay,
Yeah.
so now you'll see a wait of some kind, but sometimes a conditional wait. A wait says finish the work on the matrix if I need to. Well, I don't really have to wait. There's several things about the matrix that can have pending operations to them. A matrix can have zombies, which are pending deletions. A matrix can have pending insertions, which are called pending tuples or just pending. A matrix can be jumbled. Now, why do I use the word jumble? Well, jumble is like out of order. That means, say, every row of a CSR matrix, a matrix is finished if all the column indices in every row are sorted in ascending order. That's my CSR format for a finished matrix. Why? Because sometimes I need to do binary search on the matrix. Well, some algorithms naturally produce a sorted output. So I can say it's sorted. But I don't use the word sort because sort is overloaded, and if you grep for sort, you'll find it everywhere. I use the word jumbled instead. So you might say wait if jumbled, or just wait. It says finish everything. Pending zombies, kill the zombies. Pending insertions, pending tuples, stick them in, assemble them, and put them in the matrix. Or is it jumbled? Finish it. And that would just be a GB matrix wait, period, with no conditions. But this is one condition, because this reduction from matrix to scalar tolerates two things of pending work. I don't need to finish them. I don't need to kill zombies. Sorry, this is Zoom playing it. Zoom stuff. Like you do this, you get bubbles or something like this. The reduced to scalar is tolerant of zombies. It'll just skip over them. And it doesn't care if the entries in every row are in ascending order of column index. It doesn't matter. So I don't wait for that. So now I do assertion here that zombies are fine, Tim. Go with it. Jumbled, fine, no worries. But no, there's no pending updates.
No. Okay.
Tuples. That's what this is saying. Now, oddly enough, this is a tautology. This asserts that the matrix either has zombies or it does not. Well, that's everything. So this is actually a tautology, unless even if there's a bug in the code, this is a tautology. This is always true and
Yeah.
executed anyway. But it's a mind game, right? I'm looking at that and saying, oh yeah, I'm okay with zombies,
Yeah.
but I'm not okay with pending updates. Now I start to do the actual work. Okay, I get the size of the data structure, the size of the data type and its problem, and then I allocate it. Now this is kind of unusual. Um, this is a C variable length array, and I use this for very few things in GraphBLAS, but I do use them for one thing, and that's a scalar of a certain
Okay.
of a given data type. Well, what is the data type? Well, I don't know. It could be a built-in. It could be I have a demo with called a user-defined wild type, I called it. It's 192 byte size type. It's a monster of a type. I would have it right there. That's an array then of 192 bytes. And Z size would be 192. But I have to protect this in a macro because there's one compiler, namely the Microsoft Visual CL compiler, which does not support variable length arrays. So on Microsoft, the GB VLA macro is like 1024 bytes or something. It's like fixed.
Fixed. Okay.
And so then if you try a GRB type new on UF with that compiler, if it's bigger than that, I'll say, sorry, I can't do it. It's
Yeah.
invalid. It's too big. So it's a fixed size array on Microsoft. On other compilers, it's a variable length array and it works just fine. Initialize the scalar with identity. How? Well, just a mem copy because they're cheap and only have one of like in general, this would be a generic notion because this works for any data type. But this is one, like just do it. Um, now, now I start to make the decisions to where do I want to do this work? I have a matrix to reduce the scalar. I know the inputs are fine. There's no pending tuples now. I've killed them. I'm ready to compute. How do I want to compute this? Where do I do it? The first decision I make is, do I want to do it on the GPU? Because that trumps everything. If I really want to do it on the GPU, do it there. And I have there's there's a compile time check and a runtime check that decides to go to the GPU. The compile time check is because I might not have CUDA at all. I'm on the Mac or something on my laptop. I don't have CUDA. I'm here on my desktop. I have it. So that's a compile time thing. If you remember, GraphBLAS.h has this in it. If I look at for has CUDA, this GraphBLAS.h, if you if you install this compiled version of GraphBLAS.h, this library will have CUDA because GraphBLAS has CUDA. That's what it says right there. And so this will be enabled. But then I need to decide, and I won't go into the details of this test, do I really want to use the GPU? I have it. Do I want to really use it? Because maybe the matrix is already on the CPU. Maybe it's a small problem. Just do it on the CPU. But no, it's a big problem. We'll do it on the CPU. CUDA, I'm sorry. And I'm not going to dive into the CUDA code, only to point out the fact that it's calling the CUDA reduced to scalar, but it's actually returning two things. It's either returning this final scalar, or it's returning a vector of results because CUDA couldn't do it all. And it depends on the monoid. Like at the very end of the day, if the monoid can be supported with a CUDA atomic across thread blocks, then I'll do it to a scalar. If I don't have that, then I have to reduce every thread block reduces their work to a single scalar, and I stick the result in a final output vector V. And then I say, oh, did I do it to a scalar? Great, do it. Oh, if not, this code is recursive. It's like you've got more reductions to do, keep going. There it is. Reduce the vector to a scalar. How? Same decisions. And it's only going to go down 2 levels, typically. It could continue to do it on the GPU if you have enough thread blocks.
If it's big enough vector, right? Yeah.
Right. Now, each of these methods, of course, in GraphBLAS return an info, and I use the info all the way down to the very bottom level of GraphBLAS, the info return. And this info is a little bit different. There's an info value called GRB no value. And this is only used internally. Well, GRB no value is used by like extract element. Give me an entry. And I'll have to say, well, there's no value there. So I return GRB no value. But I use it, I overload that case to handle the situation where a method has been called and it refused to do it. And that's no value. So I may call the CUDA, I may call CUDA reduced to scalar, and I might look at this and say, something happened. Either the JIT failed to compile, or I can't actually do that type after all, or something happened. Usually it would be that JIT compilation error, maybe. But this is not yet a permanent error because I have other kernels that can do this. And that's what happens here. It's like, okay, I still haven't done it yet. Keep going. So you'll see in making these decisions, I'll know if I have to keep going and looking for a kernel to do the work. Like, you can do it? No, I can't do it. Oh, well then, if you can't do it, return no value, and I'll keep trying. It's not a fatal error yet. So if you still need to do the work, okay, well now we call now we're going to do, now we're on the CPU, but how do we want to do it on the CPU? We still have a decision to make. Now I'm committing to OpenMP on the CPU, so I do my symbolic analysis. It's 6 lines of code to decide how much work, how many threads I'm going to use. And I'm going to reduce it to a scalar. And well, there's nothing to, like, they're all zombies, so there's nothing to do. If it's this is a special kind of kernel that I'll often have. It's the ISO kernel. This kernel doesn't care what the data type is. Well, it does actually. I'm sorry. Um, the ISO kernels are producing a matrix that's ISO valued. And these don't go to the factories. These are their own kernels. They're only structural. But they have one number, one data value to compute, which is the ISO value of the output matrix. Does not check, it's not, I don't use this if the input matrices are ISO valued. I use this if I determine that the output matrix oh shoot, this is on input, I lied. This is a kernel that's checking, it's conditional on the ISO valued status of the input matrix A. What is ISO? I haven't described that yet. The idea of an ISO valued matrix is a way of handling in a matrix the notion of, say, unweighted graphs, for instance. What do you do with an unweighted graph as an adjacency matrix? Oh, it's zeros and ones, right? If it's zero not there, or sparse, so it's an entry that's not there, and an entry that's there, and it's a one. So all the entries that are present is a one. Well, in the data structure for a CSR matrix, you have an array of size, say, 1 billion, if you have 1 billion entries, for the value of each of those entries. Well, they're all equal to one. That's ridiculous. I don't need to store 1 billion ones. I just store one of them with a flag that says they're all the same, ISO or ISO if I pronounce it in the Greek. They're all the same. So I have an array of size one. Well, I'm reducing 1 billion ones to a scalar. I can do that with log2 calls to the monoid, with any monoid. Now I could change a plus into the times, because it's 1 times 1 billion if I have 1 billion entries. If it's reducing a product, I could convert x to the n. I could just multiply into power. I don't do that. I don't try to convert the operator. I just use the operator log2 time n of times, n is number of entries, log2e maybe as I should say, to get to the ISO scalar. So that's what this kernel is doing. And any monoid, it's just log n vals of a time to do. So I don't do this on the GPU anyway. Like this may decide this test would say, well, skip it if it's ISO valued. Don't bother to do it. So I haven't done it yet. Because why do reductions to scalar of an ISO valued matrix on the GPU if you're calling it log e times, or with e as the number of entries in the matrix? You got 100 billion entries. You have to call it what? 40 calls to the operator? You're not going to do that on the GPU.
Yeah.
That's ridiculous. And so that's what's happening here. And this test happens before. I'll have an ISO kernel usually, which will happen before the factory cases, because this is a little bit different. It does depend on the data type and the operator, but it just uses function pointers and memcopies because it's so fast. There's so small, little work to do. Now I make the decision, do I have a factory kernel for this? And this is a big switch case, but it's only going to happen if the type of the matrix matches the type of the input type of the monoid. Like if you have a double matrix and using a double monoid. I don't do typecasting inside my factory kernels because the combinatorial explosion, there's too many of them. Now I again have a file time check and a runtime check I'm actually going to use them. The runtime check is only for debugging inside MATLAB. I can turn off the factory kernel. So this is why it's a macro. I don't want to put it in the libgraphblas.so, so it's not there. But if I have any factory kernels enabled, I have what I call a switch. I have two phases for this factory kernel. I have a thing that says who's the worker for the switch factory, and then I say launch the switch factory. And whenever I do this in the code, I always say launch the switch. Launch the switch factory. It's all over the place. And I'll say define the worker. It's all over the place. Okay, it's a similar pattern. The worker is a macro. And then the switch factory is just a switch statement that'll plug in that macro And depending on, oh, it's this monoid, it's that monoid, it's this data type, for every built-in monoid of every type, of which doesn't matter. I don't know how many there are, but it's a bunch. Okay, so that's the factory kernels. Do you want to dive into one of those to see what it looks like, or
Yeah, I
no?
guess we could look at like plus or.
Okay, let's do some FP64. Okay, so now I'm in the factory kernel. Okay, so well now first, though, I'm still in reduce because I have to call the reduce factory. This is factory, and there's only one file called the reduce red factory. Now it's just a switch case. For two cases, there's the non-Boolean case and a Boolean case, and they're just switch. I call them switch factories. This is a switch factory, and it's multiple nested because it's based upon the opcode. Oh, it's the min opcode. Now I've basically already converted the built-in. I have an opcode, which is an enum for every built-in operator. And I have also an opcode for every user-defined. It's just user-defined. It's just all user-defined have the same opcode. But if it's the min, let's do the plus. Here, it's plus. The binary op is plus, but there's 13 of them or so. 1, 2, 3, 4, 8. I guess there's 12. Oh, there's 13 types, including user-defined types. There's 12 built-in types, right? Isn't that 12? Yeah, there's 12. In the spec, there's 10. I add 2 because I treat complex float and complex double as built-in intrinsic types, which are in the family of types that can typecast one to the other. In the GraphBLAS spec, there are 10 of these types. They're either integer, unsigned integer, or floating or double that can typecast between themselves. And I add to that the complex data type. And I really argued that that there should be a GR, a complex type in the spec, but there's not. But for me, it's a first class built-in object. So so if I'm doing, say, FP64, I'll go to this switch case, I'll go to this worker, the reduce worker that's going to, and this is a funny macro parameters, but what am I doing here? Well, this is calling a method whose name is defined by this macro. See, there's the operator and the name of the data type of the A matrix called A name, and it is plus FP64. So this is calling GB red underscore plus underscore FP64. Okay. That thing now is one of the factory kernels. If I look for red, all the reduce methods, it is red plus, it's sitting right here. It's going to call this method. Okay. And there it is. There's the method. It looks really short. What does this kernel do? This is a templatized factory kernel, and it's templatized with these macros at the beginning. That's the style here, where I'll have macros, and some of these macros are in these include files here. Like these are macros for all monoids. Every monoid shares these definitions. So what kind of operator is this? How do I do the summation? How do I do z equals f of z comma y? Oh, it's just z plus equals a because it's plus. How do I call the adder if I want to break apart and not write it as plus equal, but write it as with possibly 2 parameters for the input and output values? Oh, it's the input value of z plus a. There's the plus. How do I get a value from the matrix and do the update as a single step? Oh, it's z plus equals data value. Okay, so then basically inside this code, which you'll see the templates down here, you don't see this sort of computation. You see all these uses as the macros: add, update, get an update. Okay. What
Because
about
every
possible?
operator will be different. Yeah, and maybe we
Every
can
operator will be
contrast
different.
this. When you're done with this, maybe we can contrast it with something like min after this.
Oh, yeah, well, that would be super simple if I just do a diff between the red plus and the GB red min FB64. There, that's it. Okay, there's the update for plus, there's the update
Yeah,
for min.
right.
Now you notice this is a little bit different. Um, I wanted to, this turns out to be slightly faster than calling f min. This is the floating point min. And this is a little unusual um, because this is a NaN detector, and I want to have my NaN behavior be the same. Um, other macros I have in there that says, well, give me the identity, give me a scalar, a C scalar that has the identity value initialized to it. Well, in both of these, they're the same, except, oh no, I'm sorry, they're not the same. They're both double, but the plus identity is 0, and for min it's plus infinity.
Right.
And this is an optimization that depends on the monoid itself. Plus and min uses different sizes of sub-regions that they're going to sum up the same in a chunk of work inside the algorithm. So I defined the panel size dependent on that. I have another set of tests in the code. Let's look at this code again, which decide where is it? Here. I have ways of disabling, and there's a big file called the control.h, gbcontrol.h. FalconDB uses this because they don't need all the data types as built-in factories. They wanted a smaller binary, and they also wanted to speed up the compile time. And I thought this is a good idea. I should be able to turn off some of my factory kernels and not compile them. And that's what this allows you to. You can predefine, you say, look, I don't want any plus operator. That's kind of extreme. So all plus monoids, the plus times summary then is no factory kernels for this. That's kind of extreme. No float, no double, sorry, no double. Okay, or no plus FP64 monoids. Any of those will turn off this particular monoid. It'll disable it. If a monoid is disabled, it just returns again no value because you didn't compile it in. GRB value says I didn't do it. Go away. So this function still exists. It's still called reduce with plus FP64. The code, that function is still compiled, but it becomes a single line of code. And it says, sorry, we didn't do it. And then otherwise, okay, now I have to do it. Well, there's two methods to do it. I have two templates now. These you'll see also in the JIT, and this gets now into too much detail. I don't know if I want to dive this deep into what is the actual algorithm for doing reduction. Maybe we don't want to go that far. But it's a parallel reduction, and there's two of them. There's two of them because the algorithm is slightly different if there's zombies or if the input matrix is bitmap. So I use a simpler algorithm that can tolerate those variants. Otherwise, I can use a faster method, which is more blocky, and even on OpenMP, it's nice to do that. It's a slightly different algorithm, but it's slightly faster. It
Cool.
is significantly faster. So
Yeah, we can stay fairly high level for now.
one.
Yeah.
Okay, let's not dive into those. But so that's this decision. This might come back and say, sorry, no value. Why? Because, well, it's not in the switch case. Maybe then info is still no value because it was initialized as no value before. Or maybe I called the worker and the worker said, well, you've turned off int eights. You don't get it. And it says no value. So, I still haven't done it yet. If you haven't done it yet, how do you get to this if no value? Well, either you tried the factory and it wasn't there, or you came up here and you said, well, there are no factory kernels. You see, here it did it, but there could be no factor kernels, or maybe you have typecasting. You're summing up using the double FP64 a matrix of int 8, and that's not in the factory. So okay, prior to the JIT, this wasn't there. Prior to the JIT, well, I can't do it in the factory. I got to use the generic kernel. Well, now I can use the CPU JIT. But you notice the order of tests. It's the CUDA JIT first, because that trumps all if I have it. Then the factory kernel, well, actually ISO kernel is another case in there that happens. But this test here says, oh, it's ISO valued, back off. I'm going to let the ISO kernel down below do it. But the CUDA gets the first dibs on the problem. The CUDA can say, nah, go away. Do it because it's ISO. A is input. A is ISO, or it has too many. It's all zombies, so forget it. Tiny amount of work to do. So, or the factory kernel. Well, see, CUDA will take over from the factory kernel for sure. Most of these, yeah, it'll do any of those factory kernels instead. So it takes precedence over the existing factory kernels because this is a factory on the CPU. And presumably, if the CUDA thinks it's faster, it'll do CUDA. Now, how will the CUDA know? How will CUDA know it's faster? Well, currently it's a hack. I just have it's in production, not in production. So I have a hack that says, "Oh, if I have a CUDA kernel for it, do it, or never do it on the GPU, or try to make a decision." The heuristic in the end will be, I'm going to keep track. I have unified shared memory I'm reusing, so I don't have to do any CUDA mem copies, which is wonderful because it's already crazy complicated. Copying memory around in CUDA, it's sort of like we're back in the days of overlays. Did you ever program overlays
No.
before virtual memory existed? I did. It was a nightmare.
Well, but
Okay.
I've used CUDA before unified memory existed, so I feel your pain.
Yeah,
Yeah.
yeah, that is
Yeah.
just as painful. Okay. And so, or as bad as that, or maybe worse. So we don't have mem copies, but the memory does move around, and that's expensive.
Yeah.
So my plan, and I don't have it implemented yet, but my plan is that within a matrix to keep track of, well, where's the last time I touched this piece of the matrix? Because the matrix has several different arrays inside of it. And so which of these four pieces, here's a piece of this matrix, where do I think it is? Last time
Mhm.
I touched this was on the GPU, so it's probably still there. And that'll then up the chance that I would do this to work on the GPU if it's already there. If it's not already there, maybe I'll just do it on the CPU. Or maybe if it's a huge problem, it's a matrix multiply, well, move it to the GPU anyway, because it's big enough.
Mhm.
But if it's a small problem and it's on the CPU, just do it there. Even if it's a matrix multiply, it's faster than moving it to the GPU, doing it and moving it back.
Try and keep it
So
sticky.
yeah, it's going to have some hysteresis to it to keep it sticky.
Yeah.
And
Of
there'll
course,
be a
then there's like
GR,
oscillating and other,
yeah.
well,
Well,
yeah.
there will be some GRB get set options to say just keep this matrix on the GPU, please. Because yes, this is a trivial operation, I know, but reduce it on the GPU because the very next thing I'm going to do is use it on the GPU anyway. So just move it now, even though it's more expensive at the moment. I don't know that as inside GraphBLAS, but the user might know that. So they'll have some get set operations to say, I would like this operation to do. This matrix needs to live on the GPU or never on the GPU or whatever. Or Tim, you decide, and then I'll try to make a decision. So that's what this CUDA branch purpose heuristic is going to be there. Right now, the heuristic is pretty cheesy. Um, um, so now we come to the CPU JIT. CUDA itself is always a JIT. I haven't walked you through the JIT yet because the CUDA is actually up here. Um, this code right here will talk to my JITifier. It used to talk to the NVIDIA JITifier. We threw that away because the JITifier is limited. It uses NVRTC and it only JITs the device launches. It doesn't JIT the host code that calls the device license launches. But I need to
Mhm.
JIT that too. So it was a mess. It was limited in what it can compile. Now it's just so simpler, so much simpler. But I didn't walk you through that at all. But let me walk you through now the JIT on the CPU. So now I
Well, I just
call,
want to give you a quick time check. It's six
oh
to,
yeah, it's almost noon. I'm good if you want to keep going.
let's go. Yeah.
Yeah. Okay, so reduce to scalar JIT. This is what I call a JIT wrapper, and it ends with the name underscore JIT. And the JIT wrappers for the moment, and I might move these around. I might put this particular JIT wrapper could go inside the reduce folder, and it would be just the same. The thing about these JIT wrappers, they're very similar to each other. They always have the same structure. So this is now, I don't have it done in the factory kernel, do it on the JIT, but on the JIT, like I've already allocated workspace for the task. I already know how many OpenME tasks and threads. I've done some symbolic analysis for this reduction first, but the goal here is with that extra stuff I've already computed up above, which is true for any monoid, any data type, reduce the matrix using this monoid to the scalar z. But please do it on the JIT. Okay, that's this method. And so what this method has to do, and this has to be done either, I don't care how long it takes because I have to call the compiler, or load a binary from disk, or if I've already done that, it has to be super fast. So the first thing I do, now I'm talking to the JITifier, and that JITifier, FY, not FYI, just FY. Every JITifier method has the letter FY in it. If I look at the JITifier, they're all verb. What are these? This is an adjective turned into a verb or something like that, or a noun
Yeah.
turned into a verb, whatever. The phi. Okay, I have to encode.
Verbified.
I verbify it. I have to encodify the reduce. What does encodify do? This thing is charged with doing two things. It comes up with this encoding, which is a very small structure. It has a sequence of bits that describes the particular reduction I'm doing and the kernel I'm using, and potentially like what kernel? Oh, it's the reduced kernel. And what monoid? Well, this will be all encoded, and it also comes back with a hash value. Okay, which hashes the entire problem. And it's a 64-bit hashed value that hashes everything about this problem into one hash number, because I have to have a hash table of all my function pointers. So this has to happen super fast. I have to find the function to call. It's a function pointer. Okay, so I have to first encode it, then I pass it to the JITifier that's going to load, and this is maybe a misnomer. It's going to either look it up in the hash table and realize, and I won't dive into the JITifier load. That's too much work. The JITifier itself is a huge beast.
Mm.
It's 9,000 lines of code to do all that. But the JITifier has to do this encoding, which then encodes the different families of kernels, like apply, assign, build, EYs. These are top level things, and reduce is one of them. They may, like the semi-ring, like MXM, will have to encode enumify a monoid and a binary operator. Reduce will have to encode just the monoid. Then they'll share that code to enumify the monoid into a bunch of bits. Once I've enumerated I've come with a single number that defines which reduce I'm talking about, I have to load it or compile it if I don't have it loaded. And what am I looking for? I'm looking for a kernel called JIT kernel reduce. So this is going to potentially call JIT kernel reduce. That's what this is going to compile if it's not already compiled. It's going to make a specialized copy of this and compile it if need be, or load it from disk if it's not already there. And what it's going to do then is, by default, that these JITified kernels go in. So it's going to compile one of these. These are the templates. It's going to compile this JIT kernel reduce. It's going to compile this code. This is just for comments only. It's just a very, it looks like that factory kernel that I showed you before. It's got those same two templates.
Mm-hmm.
Okay, but it has now a compile time test. Do you have zombies, and is you bitmap? Okay, that was a runtime test for the factory kernel. It's now a compile time test. Why? Because these are now macros I've constructed. And let me show you what one of those looks like. So this is a template file. It's been specialized. Here's the top level. Here's what I put in your home folder. .SuiteSparse, and you can change this location. And on Windows, it's in your local app data or whatever, user app data place. It's always made unique by the version number of GraphBLAS. So if you upgrade to GraphBLAS 9.3 from 9.3.2 to 9.3.4, I throw away all those kernels. I recompile them. I have two places. I put the source code here, and to manage the space, I just bucket it in directories by the last 8 bits of the hash code.
Yeah.
Just to make the files smaller. But here's a bunch of kernels I've already compiled, and let's look at some reduced ones. Let's look at, I don't know which ones these are, but I'll just pick one. And it's got some, that's the encoding. It's not the hash, it's the encoding.
Mm-hmm.
And because they're kind of all, this is the 3.1 and the 3.2. These are very similar kernels.
So
I don't know
you
what this,
scan all these when the library loads to figure out the hash table?
not when the library loads, no. When you call for it. I don't go
Oh,
back,
when
I
you
don't
called.
scan this. When you call the method, well, this is the code I'm going to compile. So if I don't have this, the JITifier will write this file. So what I have a
I see.
notion inside here is there's a numify and codify. And then I say, well, is it my hash table? Oh, no, it isn't. Darn it. Okay, I'll write this file. How do I write this file? I call them macrofy methods to macrofy a monoid. That's what the macrofy mono does. It spits this out into this file.
And this is
This is
and
constructing the
bool.
macros for, logical and of a Boolean matrix, reduction of a Boolean matrix, or using the Boolean operator, logical and, to a logical scalar, to Boolean GRB bool scalar, or a
Mm-hmm.
bool C scalar, either one. I don't care now which one that is. And so this defines that monoid. What is the add? Oh, it's a logical and. What is the update? Oh, it's Z and equals Y. How do I get the identity value? Do you have a byte can you do memset?
Yeah.
Is the monoid terminal? Yes, because and short circuits. The
Mm-hmm.
moment you see a true, you can stop.
Right.
Some algorithms, in particular reduced to scalar, are going to exploit that and check, and will quit the work early if anybody sees a logical true. We stop.
Or a false, and right, the moment you see a false, you stop.
Oh, sorry, false. I got it
Yeah.
backwards. Yeah,
Right.
because the
Or
terminal value.
would be true. Right. Yeah.
Yeah, I'm sorry.
Yeah.
The
No,
moment you
it's all
see
good.
a
Yeah.
false, I got it backwards. I'm
Yeah.
dyslexic. Sorry, that's the terminal value. Give me a constant equal to the terminal value and check the terminal condition, or break if, so these are all macros that define how do you handle the terminal condition. If the thing is not terminal, these would just be empty statements. So these are everything about the monoid, including even the CUDA stuff, because this same file is almost identical if you did it in CUDA. The macrofy is identical for CUDA and for the JIT. Same header file. Just that you're going to have a CUDA kernel that's going to do all this stuff, use all these macros to do its thing. Okay, then I'll have to also macrofy the matrix, the input matrix. What is it? Oh, it's a full matrix. But wait, look at that. It's a double matrix. Well, that's weird. Well, you're using logical and on a double matrix. Why not? Because it'll typecast. How is it going to typecast? Well, whenever you load in the matrix value, you've got it. This does the typecast from double to bool. There's the test.
Mm-hmm.
And I didn't just do paren, double paren, because the NAND behavior is weird, I think. I wanted NANDs to be true, and I'm not sure if NANDs are defined. Like if you to typecast a double NAND to bool, what do you get? I think that was a weird thing. So I wanted it to have control over it. So that's my typecast. And then there is the template code that's now been specialized. It's going to work on that kind of matrix and that kind of monoid. And there's the single method that's going to do it. So this is going to construct, I'm going to compile this and create a library with 2 entry points. This is, which is this? It's GB. So if I go to lib 31, reduce. There's the compiled library. If I do, if I look at it, no, what is it? NM,
Yeah.
NM on it. Okay, what's in the library? The library has two user callable functions, and they always have the same name. One is the kernel itself. It's always called gbjit kernel, because I don't need to specialize it. I know which kernel I'm talking about. And this is the method and it's calling it right there. It's always called gbjit kernel. The loader, the JIT loader, might just find it in the hash table, and that has to be super fast. That function pointer, which is the DL function void star right there. It's returning it here and then calling it. First, I have to typecast it to that particular prototype, which the prototype, I define a macro for every prototype in my JIT. And the reason is because I have to use it in several different places. So there's the function pointer, typecast, a void pointer, typecast to this particular kernel, which has this signature. And every JIT kernel will have a different signature. But there it is in the library. The library also has another callable function called the query, JIT query. And then it's got all this OpenMP parallel stuff, and that's just the compiler put all that stuff in. But as far as I'm concerned, it's only got the two things.
The capital T codes are the public interface. Yeah.
Oh, right. Yeah, capital T. There's only two capital T's in here, and I guess an NM you can ask for just those. Okay, so what are those doing? Well, this is the JIT kernel, which is defined here, and I'll explain what the runtime difference is. And the other one is the JIT query. Okay, the JIT query is useful because what if if I looked at a user-defined data type. Oh, there's no. Shoot, let me run my Gauss demo and compile it. So here I'm running a program called Gauss. I've got the burble turned on. It's actually compiling a CUDA kernel right now because I didn't have it. It's compiling all these kernels. It's going to take a while the first time. It's compiling a reduction. There we go. And here there's burbling the compile command, no less. JIT compiling with NVCC. I'm compiling another kernel called the column scale, a matrix multiply kernel. It's crazy slow.
These are the integer complex values.
Yes, the Gaussian is integer complex. So I'm compiling a bunch of kernels. So, and now if I rerun this, look, now I've got all these kernels. Okay, and there's a reduction on, that's on CUDA no less. I didn't want to do a CUDA thing. Well, why not? We'll do a CUDA thing. It doesn't much matter because they look the same. If this was CPU, the only difference is this would be different. It would not be there. There's a CPU kernel that wouldn't be there, and this would be JIT kernel reduce instead of CUDA reduce. Otherwise, it'd be the same. But what I wanted to show you was the prototype, the query function. Why is this useful? What I do here is I want to have a way of querying. Once I've compiled the library, I want to ask, well, this is a user-defined data type. I can only call it the type called Gauss, let's say. Well, what if the Gauss type changes? Do I have to like hash the string that defines and how do I know that it may change? Like you may compile Gauss, the Gauss data type, or the Gauss operator. This is the Gauss add. What if you go and decide to change that operator? Like, here's the operator. How do I keep track of that? Do I have to hash this entire and put it in my hash table? What if you have a collision? You know, it's really dicey. So what I do is I put the data type in here twice. I put any operators in there twice. First as a C string, or CUDA in this case, string. String as this is static device inline as a compiled CUDA code, or if it's on the CPU, a compiled static device inline function. Compiler reads that, but I need this. I put the function in there twice, once as a compiled code and once as a string. And the only purpose of that string is to return it from the query. okay, query, what's your hash function? I keep track of that. Who compiled this? This is
The
for
version.
GraphBLAS
Yeah.
930. And what are your definitions? What is the user type? What is the user function? I return it there. And there could be 5 of them. And check to make sure that the identity value hasn't changed. What's the identity value? It is, where is it? The monoid identity value is an array of 8, a thing
8
of 8
zeros.
bytes. It's 8
Yeah.
zeros. I can
Yeah.
initialize it with a mem set because this is true. It's 8
Because it's two
zeros. And
64-bit integers that are zeroed out. I got you.
exactly.
Mhm.
If it's a more complicated data type, I may have to copy a bunch of bytes over. And so this just says, well, this gets passed in the identity value or the terminal value that I think I have, and this compares it and returns back true or false. And so the query then, if you look at the Gauss demo, actually exercised this at the very beginning. If I run the Gauss demo again, it says, oh, you've already compiled this, no worries. But then wait a minute, I'm compiling. Now I'm compiling with CMake just as an exercise. I loaded in, I did the JIT query. I said, and my GraphBLAS is saying, Tim, you changed the Gauss type on me, or the operator on me. I have to recompile it. And I'll do that, check that with the query. And so I'm recompiling on purpose because this demo on purpose exercises this feature. And then the rest of it, I say, oh, you've already got it. You've already compiled it. Just load it from memory. And the query is expensive. I don't want to call this every time I call a kernel. I call it only when I load it from memory. So I just compiled it, I load and check. Or if it's been there from last week, I load it and I check the query then. The other thing I have, and again, this looks almost identical on the CPU as it is on the GPU. So I just have it here in the GPU, but let me just look at let me look at one on the CPU. Like, I don't know. Here's a matrix multiply kernel. Okay. Has the same sort of thing. Well, I didn't describe the following. I have 2 notions of a JIT kernel, both for CUDA, although it's not quite working yet, and for the CPU. There's a JIT that I either compile at runtime or I load it at runtime. And there's also a thing called the pre-JIT, which sounds kind of weird, pre-just-in-time compiler. Okay, let's say this kernel, oh, wow, that's a really important kernel. And I don't want to, I'm in, say, FalconDB, and I run my FalconDB, I turn on the JIT, I let it JIT all these kernels. Okay, so I JIT all these kernels. I JIT a bunch of kernels. And then I say, okay, those are my JIT kernels. I don't want any more. That's it. Okay, and I don't like some of them. I like, some are important, some, that's not important. This one is. Pick and choose as you like. I'll just choose them all. I'm going to copy them all. I'm going to do C star star star.c. Take all those JIT kernels just on the CPU, please, not the CUDA ones yet. And I'm going to do the following. There. Sticking back into GraphBLAS. That is all you have to do. And I'm going to go to GraphBLAS, back to my library, and I'll compile GraphBLAS again. But CMake says, oh, looky, there's some JIT kernels here. Hang on, I got to compile them. Whoops. Oh, it broke.
Yeah.
Okay,
Well, we're looking at a branch here. You got changes in flight, right? Yeah.
yeah. Shoot. Okay, the reason this broke was because
You moved it.
I moved my files around, and now
Yeah.
it's not finding it. Okay, darn it. Okay. All right. I can fix
Well,
that
like I
really
said, we could
easily.
do a whole session on the JIT, so we can.
Yeah, we can.
Yeah.
But the idea is what'll happen is all these JIT kernels get baked into the libgraphblas.so. They're still on GRBNet time put into the hash table, but now they're always there. They're never unloaded. And I can turn off the JIT now. And now you have specialized kernels for your application that will run your application fast without needing the JIT at JIT time. They're baked into the GraphBLAS. And it's that easy to do, what I just did. And in the configuration, I have just built a table just now. This just got configured by CMake. All those kernels, there's the prototypes of all your kernels. And then there's a bunch of them. Here's the prototypes for the query functions. And then here's a table of the function pointers. And then here's a table of the function queries. And here's a table of all the names of the function. And I have a function at the bottom. The sole purpose of it is to return to GraphBLAS. Here you go. Here's your 474 JIT kernels that you wanted to pre-JIT. Here you go. A bunch of function pointers, 2 function pointers and a string. And GRBNet, I hash them. And now I can treat them as if they're now JIT kernels that I had it compiled at runtime, but they're baked into GraphBLAS. So it's very easy to add to specialize GraphBLAS to with the JIT. Run the JIT, grease lightning, find all the kernels you need, slap them in, and you're done. You can now turn off the JIT for production use if you like. You can leave the JIT on in production, but if you're like Falcon DB, it's like, no, don't worry, don't do that. And what will happen in the code? Let's go back to the code now. So I call the JIT, great, it works. Let's see, GraphBLAS, source, reduce. Where was I? I was in reduce to scalar here. Okay. Those pre-JIT kernels will be used here as well. And if you've turned off the JIT at runtime, the pre-JIT will say, oh, I have it, great. What if you don't want to copy all 474? What if you do something different? Oh, fine, this will not do it. It'll say no value. I don't have it. And I can't compile it because maybe you've turned off the JIT. Okay, so something happened with the JIT that said I can't do it. Whether there's a compiler error and a user-defined data type or user-defined operator, or there's 5 steps of the JIT. There's features that the JIT's turned off completely. The JIT can only use pre-JITs. The JIT can load but not compile. The JIT can compile and load, and there's 5. I forget what all 5 of them are. But maybe the JIT refused to do it, and there was no factory kernel for it. The JIT refused to do it. Somebody's got to do it, and that's the generic worker. Now what I do is all of those macros that I need to specialize the method, they're all mem copies. Like, how do we declare the identity value? I have to do a mem copy from the monoid identity. How do I copy the scalar to an array? How do I? Now this is really hacky. I've improved this later on, but okay. So how do I get A and update? I have to call the function pointer. How do I? And then finally, I include a template, but this template now is the same template that I'll use in the JIT kernel, this one, or the factory kernel, but now the specializations are mem copies and function calls. So they're slow, but it's the same code. And that's true for all my generic methods. It's the same template. It's just that those macros that define the operator and the data type and how do you do an assignment of scalar to scalar, it's now mem copies instead of equals. So instead of this is slow. Over here in the factory kernel, it's that, which is way faster.
Yeah.
So that's the very last step then, is the generic kernel. And sometimes I'll put this whole ugly beast. This is a bunch of 230 lines of code. And whoops, no, the generic case was 127 lines of code. This really kind of belongs in its own function, the generic reduce, from here to here down to here. But I didn't do it that way. And that's it. And now at the very last step, I have the mask accumulator process. But GraphBLAS, the API is a bit unfortunate. There's an unfortunate feature to the GraphBLAS API. and it's the following. All GraphBLAS methods have a mask and an accumulator, right? And it's a GRB matrix or a GRB vector. And a mask, it's a GRB matrix or a vector mask and an accumulator operator as the output. Input output, the input output is a matrix or vector or scalar. The mask is a matrix, well, except for reduced to scalar. There's no mask, and there's just an accumulator. So I had to do my own silly accumulation right here. I can't, otherwise, all the other methods, I have a method called accum mask, and which is in my mask module. It's this method. I can't do that for reduced to scalar, but this does the very last step. This is doing the C of mask plus equals some temporary matrix. And don't always need to use that method, because sometimes the method itself can finish its work entirely, because maybe the accumulator is built into the method. Maybe it exploits the mask as it's computing. So there are conditions in which, oh, I've already done the work, I'm done, and then I just take that output and transplant it into the output result, and I'm done. So
Well, we could fix that just as an aside.
which
The
oh,
the
in the spec.
reduce, yeah.
Well, yeah, it's fine. It's 20 lines of code. No big
Yeah.
deal.
Well, is there a use to masking on a reduce? I mean, I can see
No,
it being
it's
no.
It's a scalar
Okay.
mask. Why bother?
Yeah, right.
Okay.
Yeah.
The other
Yeah.
ugly part of the GRB reduce, and this ought to be fixed. This is ridiculous. Let me show you what should be fixed. Reduce, I'm not so worried about. Okay. What is it? Say, for example, GRB apply. This is ridiculous. Okay. Vector matrix apply. Okay. That's applying a unary operator to a vector or scalar. Okay, so far so good. This is applying, this is the vector case where you're applying, let's see, a binary op first with a GRB scalar. Okay. And this is the same. This is historical. Ignore this. So this ought to be full stop. It's a binary op. It's applied to the first. So you're binding the first to a scalar. Okay, that needs a special name. So here's the operator. Here's the operator and here's a scalar. That should be it. But oh wait, we want to be able to pass in a bool. Oh wait, we want to pass in a C scalar. C scalars should be banished forever from all GraphBLAS methods. Because look at this.
Yeah.
I have
I
to like
know.
bloat them.
Yeah.
This
I
is
know Ray agrees with
ridiculous.
that as well. Ray has mentioned that a couple of times. And I think
And
like if we do a
and
3.0
look,
spec, I would get rid of scalars.
they it just keeps
Yeah.
going. This is all
C
applies because it could
scalars.
be a C scalars. Yes, you have all these variants. It's ridiculous. And now you
Yeah.
have that's vector. Now vermatrix. It
Right.
keeps going.
Yeah.
And now
Yeah.
for bind second. And now for index. There are like 89 variants of GRB apply. It's ridiculous. And look at these
Yeah.
switch cases. This is the macro I have to use.
Yeah. I don't
It's
even want to see
ridiculous.
it.
It's absurd. It is the ugliest thing. And oh my gosh, to get this to work was a nightmare. There's like two of those, but you can pass in a vector or a matrix. There is the apply with, let's see, for a unary op, binary op, two versions of that, and an index unary op, but with each kind, each type. I mean, oh, it's just ridiculous. It's just ridiculous. It's like, yeah. And you know, you have to have all these, this GB cases thing is itself a macro that has to check the C type. What is it? Oh, I have to call that particular function. It's just ridiculous. So, yeah, there's like all these variants of apply. Like they're not I mean, really? Just because you want to pass in this the scalar as a C scalar, I have to
Yeah.
have 89 versions of those codes. I mean, this is not C++, okay? You're just you have to do
Well, I
this.
get it. Like the idea came up before scalars existed, and now scalars exist. So why do we? Yeah.
Right, exactly. Well,
Yeah.
GraphBLAS 1.0, this is in 2017. I took a look at it and I realized, wait, you've got a GRB matrix and a GRB vector. Where's the GRB scalar?
Yeah.
And you could, all these variants, you could just fold them all together into a opaque scalar. And opacity is important for blocking, non-blocking, and fusion eventually, right? And it simplifies the code in API. And just use C scalars where you have to get them, like get the value from a scalar into a C scalar. Fine, do one of those. You have 13 of them, right? But everywhere else, you don't need. And it gets worse if there's two scalars. Right? No, we don't do that. We don't allow that if there's two C scalars. Like but there could have been. Fortunately, we use the GRB scalar in those cases. Anyway, yeah, it's ridiculous. Apply is such a simple thing, and there's like 89 variants of apply. It's ridiculous. Um,
Well,
and
I think
anyway,
I've personally hit sort of my mental limit.
yeah,
It takes me.
I think so too.
It's a
Me
pretty good
too.
starting session.
Yeah. So what we've done here, just to kind of recap, is you've seen the kind of the big picture code structure overview, a
Hmm.
big picture, a big picture view on dive though into a particular GRB reduced to scalar, and then walking through, okay, what do I got to do? I got to check for input value. I do a matrix weight if need be, and then I got to decide which kernel I'm going to use, CUDA, ISO, factory, CPU JIT, generic, which CPU JIT could be pre-JIT, generic. That's like 6 kernels already, or however, depending on how you count them. And then, accumulate mask, and there's your result. And then where do all those different kernels live? And how do they orchestrate it? It's there's GRB reduce, and the idea of the switch factory. Whoops. There's the switch factory. It's in the factory subfolder. The templates for the algorithms itself, which we didn't look at. And I didn't show you reduce to vector. I showed you reduce to scalar. A reduce to vector calls the matrix vector multiply, but it's otherwise, and has no JITs or templates because it just punts to matrix vector multiply.
Hmm.
Um, but what else? Yeah.
The
Um,
the organization work that you've done I mean, it's sort of like you knew in advance that um, not only would it simplify it for a lot of other people, but also simplify it for these sessions because now we
oh
can
yeah,
take it we can take it in chunks.
exactly. See, what you would have to have done is otherwise, okay, I'm very careful with my naming scheme. Those are the files we looked at. Anything with red in it is reduced, and there they all are. Those are all the files we looked at.
Yeah.
So, you know, and then if you want to look at their templates, you know, there they are. Oh, there's none, I guess. What happened? Oh, whatever. Oh, no, I just did there's templates.
Yeah,
So,
and what it
you
also
know,
means is that we can move through these kind of in chunks.
right.
Like you said, we started with reduce. Maybe, in the next session you can suggest where we go from here. I mean, obviously, I know MXM is huge.
It's
Um,
huge.
uh,
What uh, what I could suggest is a function like transpose,
there we go.
because
Yeah.
I think that it's not so huge. It's 1,500 lines of code. But what it does also start to get into is like, well, what's the data formats? Because I want to dive into the GRB matrix.
Hmm.
What's in it? And it's a fairly complicated beast. It's 4 formats by row or by column. ISO valued, yes or no. That's 16 variants already. And does it have pending operations waiting on it? If it's hypersparse, does it have a hyperhash? I have a thing called a hyperhash. How do you store a hypersparse matrix? There's these formats just they explode. How do I touch these matrices? These four fundamental formats. And so that's really important. And the descriptor can transpose a matrix, and a matrix can be CSR, CSC. Really, that's the same thing, isn't it? Like, is it this way? Is it this way?
Right. Yeah.
There's only two cases with those four options. There's actually only two instances. Do you look at the matrix this way, or do you look at the matrix this way? This is a CSR matrix that's not transposed. This is a CSC matrix that has been transposed.
It
It's
is
the same thing.
transposed. Yeah. Right.
It's the same thing. And so I exploit that. I collapse these cases down. So that requires a dive into the data structure. So transpose is another method, GRB transpose. It's also used elsewhere if I ever need to transpose a matrix on input as a temporary matrix. But then, but it also is going to start looking at the different sparse, hypersparse, bitmap, and full formats. So that would be looking at a bigger piece of code like that would be useful. So yeah, I've got some. You can saw I have a bug there. I got to fix my prejits.
Well, and curious, no promises, of course. What's your timeline for the reorg work? And
Well, it's I don't know. Hopefully, maybe this week. I'm I have it's working to the point of it's passing graph tests, for example. It's running all my CUDA kernels. It's not right. I have to get to work on my statement coverage, and that also exercised the prejit, and that would have failed, right? The same failure would have been caught there. I just dumped in some prejits, and then oops, I moved the file. The prejit can't find it. Where is it? So I gotta fix that. And so and the testing. I'm working on the statement coverage testing. I've
Mhm.
not shown you that. That's a beast. How do you test GraphBLAS? I mean, you've got some crazy operations and crazy summary, and you get some matrix as a result. How do I know it's the
Yeah, I
right
mean,
matrix?
right.
I can't pre-can all these tests. I have to write GraphBLAS twice.
Yeah, once in MATLAB, right. Yeah.
Right, I did it in MATLAB. I wrote the whole GraphBLAS spec as raw MATLAB. It's super slow. It's not efficient. It's a hack. I don't care. It stores every matrix as two Boolean, a valued matrix and a bool matrix as a dense matrix. I don't even use
That's
sparse
dense.
matrices. Yeah,
Yeah.
and but it works.
It's
And
correctness. You're going for correctness. Yeah.
exactly. And so that I can call from MATLAB, I can call my C code, get the result back, call GraphBLAS, the C library, call my stupid, slow MATLAB scripts to get the same result. Then I do if equals, if not, fail.
Hmm.
And then with that, I can do my memory, I can do all my statement coverage testing once I can do that. So that's my test. It's not a CMake test, unfortunately, because I do my tests in MATLAB. I have to have MATLAB to run it. I run the test coverage in MATLAB. MATLAB doesn't have statement coverage testing. Yeah, so I wrote it myself.
Yeah, in some hypothetical future,
Yeah.
like a more useful like Python or something would have been potentially a better choice
Yeah,
to test against.
yeah,
Yeah.
yeah. So I've thought about that. What you know, it's non-trivial no matter how you look at it. Python might have been better because then CMake could talk to Python.
And you could use
Um,
NumPy to do a lot of the dense stuff. Yeah.
well, even sparse parse. It's what's a sparse matrix but two dense matrices anyway. values and are they there or not, right?
Right.
NumPy could do
Yeah.
that
Yeah.
for any data type. Forget sparsity. That is a sparse matrix. All I have to do is report the right result. Is it there or not?
Right.
And what's its value if it's there? Well, that's two dense matrices, full stop. So I could have done that all GraphBLAS. Of course, no, I wouldn't be exploiting sparsity, but whatever, it would work. The other alternative to this is to write a C GraphBLAS that is stupid simple as possible. One matrix format, I I didn't do that either.
Mhm. Okay. Well, so the next session, I guess we'll just kind of play it by ear and see where you're at, and like you said, maybe go through transpose or
Yeah, I think going through transpose and not focusing on the algorithm so much and the JIT and all that, but to look at the data structure through that mechanism, and then look. So once you see the data structures, then look deeper into things like, well, how does the JIT actually work? How does the CUDA JIT actually work? Because you've got the CPU JIT, the CUDA JIT, and then the next JIT. Well, it's the same JITifier, but the other JIT kernels could be some other accelerator.
Mhm.
And it would not be so crazy difficult to put in. Because I mean these I don't know how difficult it would be, honestly. I haven't thought of it, but I thought about it. But I have my JIT already supports two backends, OpenMP and CUDA. So that makes it easier to go to the third.
Oh, totally. Yeah, for
Um,
sure. Cool. All right.
so
Well, I'll stop the recording here. Um,
cool.
Stop. And do you want to stop cloud recording? Yep. Yes.